What's up, Dev Juniors? Have you ever wondered how games like Minecraft can generate worlds that are practically infinite yet still make sense? It's not magic. It's an algorithm called wave function collapse, or WFC for short. And honestly, it's one of the coolest algorithms out there. Borrowing logic from quantum physics to create stunning procedural content, today, we're diving deep into how this mind-bending technique builds entire worlds from scratch. It's not magic, it's code. What's the big deal with procedural generation anyway? Well, simple randomness is easy. You can tell a computer to place random blocks everywhere, but you'll often get nonsense. Think about it. A river that descends into a solid rock wall, a path that suddenly breaks in the middle of a field, or a tree sprouting in the middle of the ocean. It feels chaotic and unnatural. The real challenge, the problem WFC solves, is achieving coherent randomness. We need randomness that follows a set of rules, creating worlds that feel organic and believable. The secret sauce of WFC starts with two simple ideas: tiles and adjacency rules. Imagine you have a small set of building blocks, or tiles. These could be pieces of a path, segments of a river, or different types of terrain like grass, sand, or forest. The real genius lies in the adjacency rules. These are simple instructions that define what tile can be placed next to another. For example, a water tile can only be next to another water tile or a sand tile. It can't be next to a lava tile. A forest tile might connect to a grass tile, but not directly to a water tile. These rules are the DNA of your world, guiding how everything fits together. Now, this is where it gets a little bit quantum. At the very beginning, before our world is built, every single spot on our empty grid is in a state of superposition. This means that each empty slot holds the potential to be every single type of tile at once. It's a flickering realm of pure possibility. We measure this state of possibility using a concept called entropy. A slot with high entropy has many potential tiles it could become. A slot with low entropy has very few possibilities left. Think of it as the amount of uncertainty in that specific location. At the start, every spot on the grid has the same maximum entropy, because anything is possible. So how do we go from this sea of possibilities to a solid, tangible world? This happens through a two-step process that repeats over and over. The first step is called observation.
Ow.
The algorithm scans the entire grid and finds the one tile that has the lowest entropy, the one with the fewest remaining possibilities. Once it finds this tile, it makes a choice. It randomly picks one of the remaining valid options and collapses the wave function for that spot. The flickering possibilities disappear, and the tile is set to its final state. For example, the algorithm might decide this spot right here is now officially a sand tile. That decision is now locked in. One piece of the puzzle has just snapped into place. And this is where the chain reaction begins. Step 2 is propagation. The moment one tile collapses and is observed, it sends out a ripple effect to all of its neighbors. This is the enforcement of our adjacency rules. Since our central tile is now definitively a sand tile, we can look at its neighbors and update their possibilities. If one of our rules says lava can't be next to sand, then we immediately remove lava as a possibility for all adjacent tiles. This action reduces the entropy of the neighboring tiles because they now have fewer options. This propagation continues like a wave, with each collapse restricting the possibilities of its neighbors, which in turn restricts their neighbors, and so on. You can see the magic now, right? The algorithm just repeats this simple cycle. Find the tile with the lowest entropy, collapse it to a final state, and then propagate the consequences of that choice to its neighbors. By repeating this loop, observe, propagate, the entire grid fills itself out, one logical decision at a time. The world essentially builds itself, following the rules we gave it. This is why procedural generation in games like Minecraft, especially for things like biome placement and complex structures, feels so natural. It's also the secret behind the incredible maps you see in countless indie games. The world grows organically, not randomly. Of course, like any algorithm, WFC has its pros and cons. The biggest advantage is its ability to generate incredibly high quality, complex and coherent results from a very small set of input tiles and rules. You get a huge bang for your buck. The main disadvantage is that it can sometimes paint itself into a corner. It might reach a state called a contradiction, where a tile has had all of its possibilities eliminated by its neighbors. There's nothing it can be. When this happens, the algorithm needs a way to backtrack, to undo some of its previous choices, and try a different path until it finds a solution that works. So wave function collapse isn't about wild, untamed randomness. It's about constrained, intelligent creation. It teaches us that with a good set of rules, what looks like chaos can actually be a powerful and elegant builder. It's a beautiful intersection of computer science, art, and a little bit of quantum-inspired thinking. If you enjoyed this peek into the world of procedural algorithms, do me a favor and hit that like button. And for more deep dives into AI, game development, and algorithms, make sure you subscribe to Dev Jr. Thanks for watching, and I'll see you in the next one.